Yes. Okay. Hold on. So, interrupt is a mechanism by which the processor is made to transfer control from its current program execution to another program of more importance or higher priority. Okay, so that is an interrupt. So interrupts can be coming from either external side or internal side. Okay, so internally can be generated or external signal uh, can be given to the processor. So external request can be coming to the processor, so that after receiving that request, the corresponding function will be operated, or corresponding program based on the interrupt signal will be executed. Okay, so the 8086 allows normal program execution to be interrupted in one of the following ways, like in an external signal uh, given through one of its interrupt pins. So there are two pins, INTR and NMI, according to the pin diagram of 8086 microprocessor. So an 8086 interrupt can come from any of the following three sources. The first one, an external signal, if it is applied to the NMI input or INTR input pin, then an interrupt caused by a signal applied to one of these inputs is called hardware interrupt. Okay, so if any signal is coming through these two pins, NMI or INTR, that interrupt is called hardware interrupt. So we have two hardware interrupt pins, NMI and INTR. The second is the software interrupt, and how this software interrupt can be implemented. The execution of the instruction INTN. So there is an instruction called INTN, and where n is the interrupt type that can take any value from 00 to FF, and this is called software interrupt. Suppose I have written and all of you have seen in the programming examples that the last line of any program in 8086 will be int03, int03. So 03, that is the n here. N is the interrupt type. So n maybe 00, maybe 01, maybe 02, and all the way up to FF. So you can use this software interrupt using 256 types of numbers. Okay, from 00 to FF. So int03, it has a special, it has a separate function. Like int00, it has a different function. Like int01, it has another function. So in this way, according to your requirement, you can apply any software interrupt into your program. So that is an instruction. That's why it is called software interrupt. INT related instruction is called software interrupt. Okay. And the third possible way is an error condition such as the divide by zero, or in any trap interrupt is there which is produced in the 8086 by the execution of deep instruction. So when you'd like to divide something divided by zero, that means there must be either infinitive, or that cannot be done in by a normal machine. So that processor cannot resume this execution, it gives certain values or certain messages over the display. লাইক তোমাদের প্রত্যেকের কাছে স্মার্টফোন আছে, যদি একবার চেক করো নিজেরাই বুঝতে পারবে 5 ডিভাইডেড বাই 0 কি দেখাচ্ছে দেখো একবার টাইপ করে। 5 ডিভাইডেড বাই 0, some smartphone has certain message like division cannot be performed, or infinitive is there. So this type of message can be displayed over your output device or display device. That performance or that operation is to be operated by the help of this type of interrupt, which is called divide by zero interrupt. Okay, so another routine or another program is there to display this type of messages, and that is called the interrupt. Okay, service routine, that is called the interrupt service routine. So that means after receiving the interrupt, the microprocessor stops the execution of the current program and calls a procedure which is known as interrupt service routine, or in short it is called ISR, capital ISR, which services that interrupt. Okay, and always the IRET instruction executed at the end of the interrupt service routine returns the execution to the interrupted program. Okay, so after every ISR execution, interrupt service execution, the last line or the last instruction must be IRAT. IRAT, I return, interrupt return. Okay. Okay, so next is the interrupt processing in 8086 microprocessor. How the interrupts are processed. So there is a one type of flow chart. It's not actual flow chart. It's a graphical. It's a pictorial representation using these blocks and arrays, so that you can understand easily how the interrupt occurred in 8086 microprocessor. Okay, so let's start the process. So after executing each instruction in a program, the 8086 checks if any interrupt has been requested. If an interrupt has been requested, the 8086 processes it by performing the following series of steps. Okay, so these are the steps. So assume this is your main program, and from the external side some interrupt has been given, interrupt signal is coming, and when main program is executed by the processor, when it receives this interrupt signal, then it stops its current execution so that it can execute the required number of instructions to process this interrupt signal. Now how this will be processed? When microprocessor resumes its current execution at that point, and it goes to process the interrupt signal, first pushes the current pushes the content of the flag register onto the stack to preserve the status of the interrupt and trap flag. Okay, by decrementing the stack pointer by 2. Okay, so you have to initialize the stack because when we are about to go for execution for a current interrupt signal, you have to load the previous instruction execution status onto the stack, so that after performing this operation, when it comes returns to this main program, it holds that previous data, so the next execution or the next instruction or further pending instruction will be executed in the normal way. Okay, So before executing any other operation, so interrupt is another operation. This is your main program, this is your one operation. So until this one is interrupted, what is the value of your flag register, that must be stored onto the stack. Okay, so for future purpose, when it returns to the main program, it can retrieve the data from the stack and perform the execution of the following instructions sequentially. Okay, so that's why pushes the content of the flag register onto the stack to preserve the status of the uh, inter flag and ref flag by decrementing the stack pointer by 2, because you have to initialize the stack pointer, and when you would like to push certain content onto the stack, you must decrement the stack pointer by 2. So every time when push instruction is to be executed, your stack pointer must be decremented by 2. Okay, then what happened, then the next is uh, disables the intr interrupt by clearing inter flag in the flag register. It is known as clear if and tf flag. So clear inter flag, why? Because you have to disable the interrupt intr line. Then reset the trap flag tf trap flag in the flag register to disable the single step or trap interrupt. Single step operation must be disabled, okay, using clearing this trap flag. Clearing means to make it 0. Okay, so inter flag and trap flag must be 0. Then pushes the code segment and ip instruction pointer. So pushes the content of the code segment register onto the stack by decrementing sp by 2 again, and then pushes the content of the instruction pointer onto the stack by decrementing stack pointer by 2 again. Then performs an interact, uh, then it performs the indirect for jump to the start of the interrupt service routine corresponding to the received interrupt. Okay, corresponding to the, because you have to load the cs and ip with isr address, then it goes to the interrupt service routine. Now it is here, okay, it is here, you have to execute, microservice needs to execute this program, and to execute this program, first save the register content in stack, other register content except the flag register. If you want to if you want to store the accumulator or the bx register or cx register, because microprocessor has limited number of registers, so the same register can be used for another program which is used in your in this case as interrupt service routine. Okay, so that's why the previous register contents must be pushed onto the stack, then start the execution of the ISR, then retrieve the register content from the stack, and then perform the I return, interrupt return. And when it is about to return to the main program, it must retrieve the data IP and CS, instruction pointer and code segment from the stack. So why it is needed? Because here it needs to store the next instruction address onto the stack. Okay, so পরের ইনস্ট্রাকশনে যখন এটা ফিরে আসবে, the পরের ইনস্ট্রাকশনের কোড সেগমেন্ট আর অফসেট সেগমেন্ট অ্যাড্রেস আর অফসেট অ্যাড্রেসটাকে স্ট্যাকে তুলে রাখতে হবে, আদারওয়াইজ এটা ফিরে আসতে পারবে। রেসিপি মানে দেন রেসিপি মানে খাবার তৈরি করার ওই তালিকা বা কিছু একটা হবে। Then pop the flag register. So it must retrieve the code segment and IP of the next instruction from where the next execution will be started, the main program. So retrieve the IP and CS from the stack, then retrieve the flag register content, and it comes to the main program and execute rest of the instructions where it is interrupted, where it is resumed. Okay, so that is the interrupt processing, and in this way every interrupt, if it is coming from the external side through any interrupt pins, or if any software interrupt has been generated. In this way the interrupt will be processed. Okay. So clear up to this much?
Yes, sir.
Yes, sir.
Yes, sir.
Do you have any queries?
No, sir.
Okay. So so now let us see how the 8086 doesn't interrupt for jump to the start of the ISR of the received interrupt. Okay, so how it is occurred. Okay, so when the 8086 when the 8086 responds to an interrupt, it refers to 4 memory locations present in the interrupt vector table to get the new value of the CS and IP here in this position. So interrupt vector table is a table. It is a table where your 256 types of interrupts. There are total 256 types of interrupts in 8086. So every interrupt has been stored in this way. 256 interrupts vector addresses are stored. Interrupt addresses are stored in this interrupt vector table. Now the size of this table is 1 KB. 1 KB. This table is 1 KB, and the starting address is 00000 to 003FF. So when any these locations are reserved. So initial 1 kilobyte locations are reserved to store this interrupt vector table in any 8086 microprocessor. Okay, so these locations cannot be used to store any program, any type of data bytes or any codes. These are reserved. These are already predefined memory locations to store the interrupt vector table. Now in this interrupt vector table, each interrupt has a specific interrupt vector address. Like for type 0 interrupt, which is the first interrupt, it needs 4 memory locations to store the ISR, code segment address, and instruction pointer address. So in for every interrupt, 4 memory locations are occupied by the ISR address. And ISR address means ISR is a one type of program routine, service routine. So this ISR has one specific starting address, one specific ending address. So there must be segment address and offset address. Okay, like if there is a main program, like in previous example here, this is your main program. So it has some starting address, ending address, and that is your ISR. Another program, it has some starting address, some ending address. Okay, so when main program is executed, your instruction pointer is changed, and it will be incremented by 1 to get the next address every time. Your segment is fixed. So when it goes from this segment to another segment to operate this ISR, which has a maybe different segment or maybe same segment but different offset address, and offset must be stored inside IP. So different IPs are there. So your main program code segment and IP has been changed from this position to this position. another code segment, and IP is there to store this ISR. Now this ISR code segment and IP must be saved in somewhere else. And what is that? Where it will be saved? That is saved in this vector table. Okay, so here the code segment address and IP address of that ISR must be stored. Suppose I have used int03, or suppose I have used int00 in my program. Now int00 means type 0, this one. So if int00 is given, the corresponding ISR must be executed, and the ISR must be located in somewhere else. So it has some address. So that address must be divided into two parts. The IP address must be loaded first in two memory location, and then code segment address must be loaded. Okay, so these memory locations are used to find the starting address of the ISR of the received interrupt in the memory. In an 8086 system, the first 1 kilobyte of memory from the addresses 00000 to 003FF 3FF is set aside as a table called IVT, or interrupt vector table, for storing the interrupt vector. Now each interrupt vector indicates the starting address of the ISR of a particular interrupt in the memory. It contains 4 bytes, in which the lower 2 bytes are called offset and the upper 2 bytes are called segment. Okay, so lower two bytes, this 0000000001, this lower 2 bytes are used to store the IP, and then next two memory locations are reserved for segment address. Again, for type 1 or int01 interrupt, 00004 and 0005, these two memory locations are reserved to store the ISR IP, and then 00006 and 00007, these two memory locations are for CS. Again, for type 02, for int02, it needs 4 memory locations from 00008 to 0000B to store the corresponding IP and CS of the ISR. So in this way, every ISR will be every ISR address will be stored inside interrupt vector table to a specific, or to a required number of by the required number of interrupts. Okay. Okay, so according this table, we have 5 dedicated interrupts. 5 dedicated interrupts. And what are the names of those interrupts? That is type 00, type 01, type 02, type 03, and type 04. These are 5 dedicated interrupts. Another 27 interrupts are reserved interrupt for future purpose. That is from type 05 to type 1F. Then another 224 types of interrupt, that is from type 20 to FF. All these interrupts are used by the programmer, okay, for defining a particular interrupt. You can use it, but you cannot use these memory locations with middle portion, which is reserved interrupt. You cannot use. And already these are you have 5 dedicated interrupts. You can use this one also. Okay, so total 256 types of interrupts are available. 224 plus 27 plus 5, that is 256 types of interrupts are available, and the number of these interrupts are from 00 to FF. Okay, 00 to FF. So is it clear? Is it clear, everyone?
Yes, sir.
Okay, so next is the interrupt types. How many interrupts are available? The lowest five interrupt types in the 8086, that is from 00 to 04, are dedicated interrupts, and these are called as type 0, which is called divide by 0 interrupt, type 101, which is called single step or trap interrupt, type 02, that is called NMI interrupt, and type 03, that is 1 byte INT instruction interrupt, and type 04, that is overflow interrupt. Okay, so these are 5 dedicated interrupts, and so I will discuss one by one these interrupts. Okay, so a type 0 interrupt, which is called divide by 0, the first one. So whenever the quotient from a division operation is too large to fit in the result register, which occurs while dividing a number by 0, or if the divisor is very small compared to the dividend, the 8086 automatically generates a type 0 interrupt. Okay, and it executes the normal operation according to the interrupt signal. So it is internally generated using the software instruction. This is one type of software interrupt. Or if it is generated automatically, then it is called divide by 0 interrupt. Okay. The next is the type 01, which is called single step or trap interrupt. Now the type 1 interrupt is used for single step operation, in which the 8086 executes one instruction in the main program and then executes the ISR of the trap interrupt. So in this ISR, we write the instructions to verify the contents of certain registers and memory locations and display them in an output device, such as any display or any monitor or any type of LEDs are there in this way. And so if the expected data are present in the register or memory location, then the 8086 can make it proceed to the next instruction. Okay, so this is a single one by one, the instruction will be executed and it gives the result. Type 02 interrupt, which is called the NMI interrupt. NMI interrupt, actually it cannot be disabled by software. That's why it is called non-maskable interrupt. It cannot be masked or cannot be delayed or cannot be ignored by the processor. Okay, so that's why it is non-maskable interrupt, and NMI interrupt is always used in emergency purpose. Okay. As for example, in power failure and or the smoke detectors, the application or fire alarm, so in this type of emergency purposes, this NMI interrupt has been it is used. Okay, always. And then next is the type 03, which is 1 byte INT interrupt, and this interrupt is produced by the execution of the INT 03 instruction, and all of you have used in your program. The last line will be INT 03, which is called breakpoint interrupt. So it is a single byte instruction which is mainly used to implement a breakpoint function in the 8086 system for debugging your program. So when we insert a breakpoint in the program, the 8086 system executes the instructions up to the breakpoint and then executes the ISR corresponding to the breakpoint interrupt. So unlike the single step interrupt, in which the execution is stopped after each instruction, the breakpoint interrupt technique is it allows us to execute all the instructions up to the inserted breakpoint in the main program. The processor then goes on to the onto the ISR address to execute the ISR of the breakpoint interrupt. Okay, and then type 04, which is called overflow interrupt. Now the overflow is set if the result of an all of you know the overflow flag is there in 8086 flag register, and if overflow flag is set, that means when it will be set if the result of an arithmetic operation on sign number is too large to store inside the destination register or memory location. So there are two ways to detect and respond to an overflow error in a program. One is uh, place the jump on overflow instruction immediately after the arithmetic instruction. If the overflow flag is set due to the result of the arithmetic instruction, execution is transferred to the address specified in the uh, jump on overflow instruction. At this address, an error routine that responds to the overflow in the required manner can be placed. Otherwise, second is the place the interrupt and overflow interrupt on overflow. So there is an instruction called interrupt on overflow, INTO instruction, INTO instruction, immediately after the arithmetic instruction in the program. If the overflow flag is not set when the 8086 executes the INTO instruction, it is treated as a no operation. Okay, it's treated as no operation. So if the overflow flag is set, then 8086 generates a type 4 interrupt after executing the INTO instruction. Now, instruction in the ISR produce the desired response to the error condition. And the advantage of having this type of instruction, INTO instruction, is that the type 4 interrupts ISR can be easily accessed from any program in a multitasking environment where you need to operate the multiple number of operations. Multiple application is there. You have to at a time you have to control 4 types of operations. Sometimes you have used 4 applications and you have to minimize your current application so that you can execute your another application. Okay, so this is called the multitasking. You have to operate multiple number of operations at the same time. Okay, so these are the functions of these 5 5 dedicated interrupts. So I have another 4 minutes time. After that the meeting will be ended automatically, and all of you must click on the same link to continue this meeting. That is the second session, so that I can end my lecture in due time. Okay, so software interrupts. So how many software interrupts are there? The INT instruction of the 8086 can be used to generate any one of the 256 possible interrupt types, which are called the software interrupt. The desired interrupt type is specified as part of the INT instruction, which is INT, like example, INT 21 instruction causes the 8086 to generate an interrupt of the type 21. If it is written as INT 00, then it causes the type 0 interrupt. If INT 1 is there, then it is called, if INT03 is there, INT03 instruction causes the 8086 to generate an interrupt of the type 03. Okay, INT03 is there, so it is type 03 interrupt. And in this way, the IRET instruction at the end of the ISR makes the 8086 to return to the main program to execute next of the INTN instruction to continue the execution of the remaining program. Okay. So the uses of the software interrupts are inserting breakpoints into the program for debugging, like INT03, you can use it, or testing the function correctness of various ISRs. Like for example, INT02 instruction can be used to test the ISR for the NMI interrupt, non-maskable interrupt, without giving any input signal to the NMI pin. So either NMI, so you can use it in two ways. Okay, two ways. Either hardware interrupt can be given through NMI pin. You have in 8086, you have NMI pin. So if any signal is connected through these NMI pins, again non-maskable interrupt can be generated. Otherwise, you can use INT02 in your program, so that software, by software means the non-maskable interrupt can be generated. Okay, so non-maskable interrupt can be coming either external side, or it can be generated by internally. So 8086 interrupt response, 8086 interrupt response, as part of this response of the interrupt, the ZC automatically clears the interrupt flag. And how it clears the interrupt flag, there are two reasons, and why it clears the interrupt flag, there are two reasons. First is to prevent a signal on the INTR. Why you need to first disable the interrupt flag before executing executing any interrupt signal? There are two reasons. First, to prevent a signal on the INTR input from interrupting a higher priority ISR in progress. If needed, interrupt flag can be set at the beginning of the higher priority ISR, so that 8086 can be interrupted by an INTR interrupt while executing that ISR. And otherwise, to make sure that a signal in the high state existing for a sufficient duration, say a few microsecond or millisecond on the INTR input, does not cause the 8086 to interrupt it again before completing the current execution or current ISR. Okay, interrupt service routine. So that's why they, because of these two reasons, the interrupt flag must be cleared.